Okay, so welcome to week 7 of Electromagnetics in Guided and Wireless Media course. And I'm Shazan Butt, and I'm the coordinator of this course. And this course is being offered by IIT Kanpur, and the course instructor is Professor Pradeep Kumar. So essentially, till now, you have basically studied a lot of things, and we are into week 7 of this course. And what you might have studied is something called as linear antenna, which is a linear current carrying element that can basically radiate electromagnetic waves in the free space. Let's say you have a current carrying wire. So if you are basically sloshing electrons back and forth in this wire, and I told you in the week 5 that how it can basically result in the generation of electromagnetic field which can basically propagate in the space. So that was essentially the concept, and you might have studied about Friss transmission formula, which is just on what factors does the radiated power depend upon. So it's about how much power is basically radiated, and you might have seen that it depends upon the certain factors, which is basically the received power, the transmitted power. It might depend upon the gain of the antennas, and it might depend upon the distance between the antennas. It might depend upon the wavelength, obviously. And then you might have studied also about certain concepts related to the I should say something called as something called as array factor. You might have studied in this week, and this basically comes when you have multiple elements in an in a linear antenna array. So in that case, you don't talk of only one antenna. So basically, you have a linear array and you have multiple antennas which are basically propagating the electromagnetic waves. And essentially, you want to know that uh, what is the, I should say, the beam pattern, the directionality of this particular, because you are exciting multiple antennas, and as a result, the radiation pattern is modified. Okay, so essentially, when each of the antenna radiates in the free space, because each of them is radiating, so there is this interference zones which are basically created. So essentially, the interference is happening. Okay, so there can be this can be destructive interference, this can be constructive interference, and depending upon that, you can basically change the directionality of it. And this is exactly the concepts in something called as beam forming, beam forming, or it's something called as when you use an array of antenna, it's basically you can steer the beam. So it's also called as beam steering. Beam steering. So essentially, if you want the electromagnetic waves to go in this direction, you don't have to move the antenna array in this direction. You basically have to apply certain phases to each of these antennas. And depending upon the constructive and destructive interferences, the beam can basically go in this particular direction. And that's what I have talked about. I guess I don't remember, it was in week first or week second. I have talked about when we talked about the basics of electromagnetics. I guess you can just refer to this lecture, but I will be slightly giving a brief introduction about what basically happens in these type of arrayed array antenna, arrayed linear array elements of in a linear antenna. Pardon me, I'm basically having cold and my voice is not sort of naturally coming as it is supposed to be. So there's apologies for that. So let's straight jump to the questions today. Today we will be solving again the questions. So let's take the first question. So the first question says the magnetic field strength is 2.5 microamps per meter. That means what is basically given is H. So essentially H of phi is basically given. Because you know now what is phi, what is theta, you essentially know. You don't have to basically think about it because you are considering a spherical coordinate system. So this essentially is basically r, this is theta, and the projection of it is essentially phi. So you have a magnetic field, and at a point theta equals to pi by 2. So theta equals to pi by 2 should be somewhere here, 1 kilometer from a thin wire antenna. So this is the distance which is basically given as 1 kilometers. And twice L is lambda by 2. What is the current that must be fed to the antenna? So you need to basically compute the current. So essentially you have all of the details that are basically required. So let's try to solve this question. Let's try to solve this question here. So you know from your basics that for a thin, I should say for a linear thin dipole antenna, you have basically the far field magnetic field can be given by h of phi. We have talked about this in the previous lectures. J I naught e to the power minus j k r divided by 2 pi r cos of k l cos of theta minus cos of k l divided by sine of theta. So you have studied this from this week 7. What are the other things? This I naught is essentially the current feeded to the antenna. Okay, r is basically the distance from antenna, and the k is basically 2 pi over lambda, and 2l is that is what is basically given is the total length of antenna. So this 2l is basically given as lambda over 2. So essentially you have l to be equivalent to, oh god, what is happening? Lambda over 4, and therefore you can write k times l to be equivalent to 2 pi over lambda into lambda over 4. So you get kl to be equivalent to pi by 2. So this is essentially the phase of this particular term, kl, inside the cos term. Now, if we evaluate the this particular term, because theta at pi by 2 is given, so we need to evaluate at theta equals to pi by 2. So essentially, cos theta will be 0. So this term should go. Sine theta will be 1. So we are left with only this term. Okay, and it will essentially come out to be equivalent to 1. So when we solve when you solve it for theta equivalent to pi by 2 and kl equivalent to pi by 2, you get h of phi to be equivalent to, just put the value of theta, you get I naught divided by 2 pi r. And this is essentially the magnitude only. And when you take the magnitude, this term will basically go. You no longer have the e to the power this k term. You're only taking the magnitude of this term. So you have I naught divided by 2 pi r. This whole equation will evaluate to be 1. And essentially you're taking the magnitude. So now everything is given basically. So now you have h of phi to be equivalent to, I guess h of phi is given. How much was it in the question? It's 2.5 microamps per meter, which is essentially 2.5 into 10 to the power minus 6 amps per meter. And therefore I naught will be magnitude h phi into 2 pi r. So r is basically 1 kilometers, that is 10 to the power 3 meters, and essentially you have 2 pi r h. So you can calculate h, this is 2.5 into 10 to the power minus 6 amps per meter multiplied by 2 into 3.1415 into 10 to the power 3. So this will come out to be in amps because this is in meters. So meter will go, and you will get the current of approximately 0.015 amps. So essentially I guess you have to report in milliamps. So I naught will come out to be equivalent to 15.7 roughly milliamps. So this is the exact answer of the question. So essentially you need to basically uh, solve you need basically 15.7 milliamps of current for this magnetic field to be of this particular order at a distance of 1 kilometers. And this is the exact answer of the question. So this is question first. That means the answer should be, okay, we have to write it in terms of pi. We have to write it in terms of multiples of pi. So we don't need to basically we need to keep it like this. And when you keep it like this, you have 2.5 into 10 to the power minus 6 into 2 into 10 to the power 3 into pi. So you have 5 into, this is 5 pi into 10 to the power minus 3. So it'll be 5 pi milliamps. This should be the equivalent of this. So you have 5 pi milliamps is the answer of this question, and that's the answer. So just give me a moment. So now this is the question first. Now the question second is, what is question second? From the data given in question 1, the average power radiated by the antenna. So we need to compute the average power radiated. We already know the current, which is basically around 15.7 milliamps, which is roughly 5 pi milliamps. Okay. Now average power radiated by the antenna, you know that it can be written as half of I naught square R. R basically the radiation resistance. Okay. And this half comes, why does this half come? Because this I naught here is the peak current. So this is the peak current. So that's why there is this half term. Otherwise, I mean, you might have noticed that you write power as I square R, but this when you write it the I as in terms of the peak current, you get I as I naught by 2 as a peak current. So it depends upon whether you take it as a peak current, RMS current, what type of a current you are basically using in this equation. So now what you have is you need to solve this. So you can compute the average current. How much is the basically the radiation resistance? Is it given in the question? It's around 73 ohms for the half-wave dipole. For the half-wave dipole antenna, the radiation resistance is around 73 ohms. Just let me cross verify it. Yep. Mm. Okay, so God. So essentially you have So essentially what you have now is everything. You can compute the average power as half of um, 5 into 3.14. Essentially that's 15.7 into 10 to the power minus 3 square into 73. So you get the value roughly of the order of 9 millivolts. And that is basically the answer of this question. So you get the average power radiated by the antenna is around 5 milliwatts. Okay, which doesn't sound much, but it is some sort of a huge power which is basically radiated. Ideally, we try to keep this number as low as possible. That's what I also told you. Because more the power, more will be the radiation coming out from the antenna, more will be its impact on certain things in the environment. Okay, ideally this number should be as small as possible. Now the question 3, the maximum power density for a thin wire antenna in the direction theta equals to 45 degree is. So note that this is theta equals to 45 degree. That means basically you are looking at a power at theta equals to 45 degree. That means in this direction. Okay, and you know that if you have the maximum power radiating in this direction, so essentially you need to look through this direction. That means your power will not be obviously maximum, it will be some part of this power because most of the power is going through these two lobes. Okay, and what you are basically now seeing again is a thin wire antenna. That means 2L is around lambda by 2, or you can write L to be equivalent to lambda by 4. And what else is given? So maximum power density is proportional to F theta square. So what is this F theta? F theta is the radiation. So this F theta is basically called as radiation pattern function. And you might have seen that this F theta can be written in terms of cos of pi by 2 cos theta divided by sine theta. So essentially it's something, it's this particular term, similar to this particular term. It's not exactly this term is similar to that of this particular term you might have seen as the radiation pattern function. And we know that if you have a let's solve the question 3 here. Let's take it from here. This is question 3. So essentially you might have seen that the power density is actually proportional to F theta square, and it is given in the question itself. This thing, maximum power density is proportional to the F theta square. Okay, and now you have theta to be equivalent to 45 degree, which is basically pi by 4. So you need to use this in this particular equation. So you can compute F theta as cos of pi by 2 cos of pi by 4 sine of pi by 4. So you get this as cos of pi by 2 into 1 over square root of 2 divided by 1 over square root of 2. So you essentially have cos of pi by 2 root 2 divided by 1 by square root of 2. So what does this come out to be? You solve this, you get this F theta to be approximately equivalent to 0.63. So I have solved it. You just need to just cross check whether this is exactly what we get. And now if you square it, because power density is proportional to F theta square, magnitude of theta square, so this will be 0.63 square. So this will come out to be equal to 0.39 approximately. So essentially the F theta at 45 degree is, so this is basically F at pi by 4 is basically 0.39. So the power density is about, so if you write it in terms of the percentage, how you can write it 0.39 into 100%. So this is basically 39, approximately 39%. So basically the power density is 39% of the maximum value, because you know that the maximum occurs at 90 degrees. So if this is the lobe, if the maximum is occurring here, and if this is the theta, at theta equals to 90 degrees, the maximum is occurring. At theta equals to 45 degrees, at this particular theta, you have basically the power density is 39% of the maximum value That means 39% of this value which you have at theta equals to 90 degree. So that means only 39% of the power is basically radiated at this 45-degree angle. Similarly, because it's symmetric, similarly it will be at this particular angle. Let's consider this as minus 45-degree angle. Okay, so that is basically essentially the concept. Okay, so oh god, what else? These are like easy questions. These are formula-based questions, and if you have studied week 7, if you've gone through week 7, I should say sessions, then you can easily solve these problems. These are just cakewalk. Now question, what is the answer? Yes, it's 0.39. So it's 0.393. Now in Fritz formula, we have the question about the Fritz transmission equation. What is this Fritz transmission formula or equation? So whenever I write Tx is for transmission and Rx is for receiving, or receiving, whatever you call it, receiver. So this is sort of a terminology in antenna. You represent the transmitting antenna as Tx and the receiving antenna as Rx. Okay, so this is sort of a terminology I will be using. Don't get confused from it. So essentially what we are trying to see, question for solution, or whatever you call it, the answer. So the Fritz transmission equation is basically it gives you the radiated power, which is basically a function of transmitted power. This is the overall radiated power. And what happened? And the overall radiated power you might have seen in the in this week 7, you might have studied about Fritz transmission equation. It depends upon the transmitted power by the antenna. It depends upon the gains of the transmitting antenna and gain of the receiving antenna. And it depends upon the wavelength and also the distance between the antennas. So it depends upon the square of this. So essentially, this is basically the transmitted power, and this is the gain of the transmitting, I should say, transmitting antenna. This is for the receiving antenna gain, receiving antenna. This is the wavelength of the specific electromagnetic wave we are talking about, and R is basically the distance between the two antennas. So you might have seen this formula a lot, which is used in week 7. I don't want to just derive this formula from the scratch. So, and you might have also seen that there is a certain relationship between the gain and the effective area. So if you have gain, you can write gain in terms of the effective area, which is basically AC divided by lambda square, where this AC is basically the effective area. And if you substitute it back in the equation, in the power radiated equation, you are essentially going to get that the radiated power is proportional to the effective areas of the transmitting and receiving antennas, because uh, you go and put this back into the gain equation here. So essentially you are going to get that PR is directly related to the effective cross section, or effective area. This is basically the effective area of the antenna. So it's going to be proportional to effective area for the transmitting antenna times the effective area for the receiving antenna. And I guess this should be the one of the options in this particular question. So it's saying that square of the distance between the two antennas. So it's proportional. It's not proportional. It's inversely proportional to the square of the distance between the two antennas. So the radiated power is inversely proportional to the square of the distance between the two antennas. It's proportional to wavelength. No, it's not proportional to wavelength. It's proportional to wavelength square. Product of effective. This is the exact answer that we are looking for. Effective area of transmitting antenna only. Not exactly. So it doesn't only depend upon the effective area of the transmitting antenna, but depends upon the effective area of the receiving antenna as well. Okay, so that is the exact answer of this question. So it depends upon the effective area of both receiving as well as the transmitting antenna. So, okay, so the essential thing is that when you are considering the radiated power by the antenna, then both of these antennas are going to matter. This is the exact takeaway from this particular question. It means that if you have this antenna and it's transmitting certain power, and you have a receiving antenna, then basically the radiated power by this depends upon also that how much is the effective area of this and the gain of this particular antenna. Okay, it's as if how much it can basically accept. Accordingly, it will radiate the power. If this antenna has a very if this antenna has, let's say, a very high gain, then essentially the radiated power here will accordingly change, and it's directly proportional to gain of the receiving antenna as well. So if the gain increases, that means the effective area increases, it can radiate more power. But if it doesn't have the I should say the power handling capability, that means if it doesn't have a high effective area, if the effective area here reduces, then accordingly the radiated power here is going to reduce. So it's the full scenario that it depends on both transmitting and receiving antenna. And this is basically essentially the Fritz formula. And there are certain approximations in this formula as well. It's a very simplistic formula, but there are certain approximations which need to be considered. And it also depends upon the wavelength square. That means if you want to transmit a 5 gigahertz signal, and on the other hand, if you have a, let's say, 2.4 gigahertz signal, and if your radiated power is basically proportional to lambda square, so your radiated power is proportional to lambda square. So for this case, you need more radiated, you have more radiated power, and here you need less, oh God, less radiated power. So essentially that means the wavelength is also important. So if you want to transmit a high frequency, or I'm writing in terms of frequency, my bad. It's my bad. Why am I writing frequency? So essentially if the let's write it in terms of wavelength. So essentially if the wavelength here is, let's say, how much is the wavelength for 5 gigahertz? Wavelength is 3 into 10 to the power 8 divided by 5 into 10 to the power minus 9. So this is 0.6 into 10 to the power minus 1. So this is around 0.006 meters, which is around 6 centimeter. So lambda is 6 centimeters for it. And for 2.5, that means divided by 2, it will be 6 over 5. So it will be 1.2, and it will be 1.2 into 10 to the power minus 1. So it will be 0.12, that is 12 centimeters. And for this, obviously, it will be double. So it will be 12 centimeters. So this is for frequency of 5 gigahertz. This is for frequency of 2.5 gigahertz. So essentially, if you have a whatever you call a Wi-Fi network of what you call as 5 gigahertz Wi-Fi network, it has a wavelength of 6 centimeters, and for a 2.4 gigahertz network, it has a wavelength of 12 centimeters, roughly. Not roughly, it has exactly the wavelength of this, depending upon the speed of light and the speed of light, electromagnetic wave, and the I should say the frequency. And that means it requires more power, radiated power, for lambda equals to the 6 centimeters compared to that of lambda equals to 12 centimeters. Essentially, that is the concept, because it requires more power than to basically slosh the electrons back and forth so that you can have a high frequency wave emitting compared to that of a low frequency. Let's say this is 5 gigahertz wave, this is 2.5 gigahertz wave, or it's actually 2.45 gigahertz. Okay, so it depends upon also the wavelength of the electromagnetic wave which is basically being used. So that's why if you earlier had a megahertz system, 92.7 megahertz, you might have heard the radio stations, and this is essentially the frequency. So this is the radio stations that we are basically using this particular frequency band, and that means it required less transmitted radiated power was less compared to that of what it is today. If it is a wireless signal or a signal coming from the base station, which is around 2.45 gigahertz or more, it depends upon what sort of a carrier is also being used. Then accordingly, the radiated power is going to basically change. So this is about the Fritz equation, and what else is there? It depends obviously upon the transmitted power, gain of the transmitted antenna, receiving antenna, and yeah, we have discussed most of these terms. So essentially, it also depends upon the distance between the two antennas. So that means if your transmitting and receiving antenna is at a distance of, let's say, distance of R1, and in another scenario, if it is distance at R2 and R2 is greater than R1, then in this case, in the first case, the transmitted power has to be more. Sorry, in this case, the transmitted power has to be if the R is less, then the transmitted power increases. If the R is more, the transmitted power goes down. That means in this case, the transmitted power is less. In this case, the transmitted power is more. So that's accordingly what basically this relationship tells you. Okay, so now what else? Question. So this is the exact answer of this question. So now let's move to question 5. Question 5. So question 5 tells you that you have two antennas which are separated by 1.5 kilometers, and they are operating at 300 megahertz, which is super cool. And it's equipped with a linear antenna. Again, it's a linear antenna where 2L equals to lambda by 2. That means L is lambda by 4. And the directivity, which is basically 1.64. And we have talked about this directivity in the week 6 in the week 6 lecture. And essentially, what we have, and 100 watt of power is transmitted, which is huge. So the power transmitted is 100 watts from one antenna. Then the received power in case of the matched load is, so you need to compute the received power. In case of the matched load means the impedance matching is perfect. There is no impedance mismatch. And so the scenario is like this. So the scenario is you have two antennas transmitting, receiving, separated by certain distance, which is 1.5 kilometers, and this is transmitting at 300 megahertz. You need to convert this into wavelength. How much will it be? 3 into 10 to the power 8 over 3 into 10 to the power 8. So this goes, so it's around 1 meter. So the wavelength is around 1 meter. Okay, so essentially the thing is that the thing is that and directivity is also given, and the transmitted power here is 100 watts. The directivity is 1.64. We talked about this directivity. Yeah, it's sort of an I should say you can have a directivity as well as if you remember when we talked about in week 6. Yep, this is the directivity. And if you write the directivity as a maximum of this directivity function, which is basically the average of u function, then the directivity can be written in terms of the logarithmic function also. Okay, yeah. So essentially, what you need to find is the received power. The received power. So you're gonna use the Fritz transmission equation to compute the received power. And pardon me, this PR is essentially the received power. It's not the radiated power. I just mistakenly defined it. It's the received power, not the radiated power. So essentially, the received power is depending upon the how much is the area of the transmitted antenna and how much is the area of cross section, effective area of receiving antenna. That makes sense because if your area of the transmitting antenna is more, it's going to transmit more power and you are going to receive more power. Okay, and accordingly, if your area of the receiving antenna is more, then it's going to receive more power. So it's just like dishes, the small dishes, which are basically the dish antennas you might be using. If you use a bigger dish, it's gonna receive more power from the other antenna. So it's the receiving power, not the radiated power. It's different. Okay, just pardon me here. I just want to correct it. So that's why That's why the receiving power depends upon the gain of transmitted antenna, gain of the receiving antenna, obviously, and it depends upon the wavelength. So if you have a higher wavelength, let's say it's this again, I'm just rewriting. So the received power is proportional to wavelength square. That means for for higher wavelength, you have you have PR more. That means the received power is more compared to that of the lower wavelength, which is basically this. So the received power will be less here. It's not the radiated power. I'm again mentioning the point. So in this case, the radiate received power in case of the 5 gigahertz will be less compared to that of the 2.4 gigahertz. And why it's the case that why it's the case that the received power is dropping as the wavelength is basically reducing. Because if the wavelength is reducing, the frequency is essentially increasing and the attenuation actually increases. So the high frequency beams undergo a significant attenuation compared to low frequency beams, and that's also the case. If you go to high frequency, it significantly attenuates in the channel compared to that of the low frequency signals. Okay, so that's why you have let's say for example, if you have here R1 is if you have R2 greater than R1, so the received power in case of received power here will be lower than the received power in R1. That makes sense because if it's closer, then it's going to receive more power. Okay, so that's exactly the scenario, and essentially it's about the receiving power. And now what we are going to calculate is going to calculate the receiving power, the power received at this particular end by the receiving antenna. It will be equivalent to transmitted power, gain of the transmitted antenna, gain of the receiving antenna, lambda divided by 4 pi r square. So again, highlighting the fact that this is the received power and not the radiated power. Okay, and now what essentially is happening is you have everything given. R is given, also frequency is given, which is one corresponding to one meter wavelength. The transmitted power is given. The directivity of each half wave dipoles is given. That means GT functions is given. That means GT equals to GR is equivalent to 1.64. So you're going to use PR will be equivalent to 100, which is basically transmitted power, into 1.64 square, which is basically GT and GR, into this is 1 meters, 4 pi into this is 1500 meters, it's square. So when you compute this, you get the received power to be around 7.6 into 10 to the power minus 7 watts, which is around 0.76 microwatts. So you see how much power is received is it's very small. So essentially you transmitted around 100 watts and this has received around 0.76 microwatts. And the loss is, I mean, how much is the loss? 99 point whatever it is, 100 minus 0 0.76. So you get this is 4 2 and this is 99. So 99.24 watts of the power it's lost. Where does it go? It either it's attenuated or it gets absorbed. This is attenuation, absorption by the atmosphere, or something else. So essentially, if you bring down the distance, then this power, this should go down and this should go up. Okay, that's essentially the concept of this particular uh, Fritz transmission, Fritz power equation, or the Fritz formula. And And it's simple, from the classical mechanics, the power transmitted will depend upon the distance. Closer they are, more power it will receive. Farther they are, less power it will receive. Now, because it's a wave, it also depends upon the wavelength. Okay, so that's essentially the case. So the received power will be 0.76 microwatts, which is a very small fraction of the power. And pardon me, I mean, again, I've done a mistake. This is not this is microwatts. So it's very small. So out of 100 only 0.76 microwatts is received. So this is essentially 7.6 into 10 to the power minus 7 watts out of 100 watts. So this is negligible power being received. So it's approximately, I should say, you should call it zero. So most of the power gets basically wasted, or it's not basically received by the antenna. Depends upon obviously the distance. That's why whenever you have, because there's such a huge attenuation, whenever you might have seen that you have base stations, if this is the one of the base station with the antenna, you have these base stations at certain distance from each other. So let's say this is the receiving antenna, this is the transmitting antenna. So the transmitting, this is the receiving. Similarly, this is another base station, and this is the transmitting antenna, this is the receiving antenna. So essentially, you have these base stations located at certain distances from each other, and they form sort of a cells, which are basically most of the time sort of hexagonal cells. So essentially, what you have basically, if you have an area, let's say you are living in some part of maybe Mumbai, or you are living in the north, then basically what happens if you have a small area or maybe a district, it's basically divided into these hexagonal cells. Whenever the base station people come, they divide the area into hexagonal cells, essentially something like this. So each of these cells is basically assigned a single base station, so that each of these cells, and it has a strict criteria of how much should be the area of this each cell, how much basically should you essentially radiate the power. So each of this hexagonal cell is given a base station, so that each of the base station basically acts like a repeater. So this is a repeater. That's why you need repeaters. It's sort of because whenever the transmitter signal comes here, the received signal is very small. So essentially, you need to amplify the signal, and you need to amplify it in magnitude and then transmit it back to another receiver. And then again, there's a power drop, and then again, there is amplification in the internal circuitry, and then again, it's transmitted. So someone making a phone call here, let's say, to a person who is present maybe on the other side of the cell, then basically what happens is that this person makes a call, the signal goes to the base station, then it is transmitted, either it's transmitted, it's only wireless here. Okay, on the other part it is basically wired. So most of these base stations are connected by wires. You might have seen those long wires going from tower to tower. But if you have a completely wireless situation, then essentially what would it mean? That the signal going to this base station is going to get transmitted to this base station, but here it will be amplified, and then it will be transmitted to this base station, and then it will be transmitted to the mobile phone, and then again the reverse process will happen if it is completely wireless. But the base stations are not completely wireless. They are wired. They are only wireless from the mobile phone to they are only wireless from mobile phone to the base station, not from the base station to base station. Okay, but there are other technologies, let's say satellite technology or other antennas, that basically depend upon not the wired technology, they depend on only on the wireless technology. Then they have to basically use repeaters in order to transmit the signal. So essentially, if this is Earth, then if this is one of the antenna, this is another antenna, this is another antenna, somebody, then this antenna transmits to this, and this antenna, there is loss, and then this has to amplify the signal. So it's essentially the repeater, and then this has to basically again send the signal to here, and then the reverse process happens in the communication. And it also happens in the satellite communication. You have some satellite here present in the orbit. So you have, yeah, it's sending the signal. For example, this antenna 1 has to transmit the signal to antenna 2. But if the satellite is not in the exact position that it can transmit to, then the satellite has to basically transmit to another satellite. So essentially, three satellites can cover the entire Earth. So that's the concept, because they can be placed at certain orientation, and they can essentially cover entire Earth, all of the positions on the Earth. So if this antenna transmits signal to here, it gets lost there is losses. A small part of it reached to satellite, and then it's amplified here. So it sort of acts like a repeater. And then it's transmitted to this satellite or the other satellite, and then again it's lost here. Then again it's amplified. So it's sort of a complicated circuitry and electronics and signal processing used. Low noise amplifiers are used. I mean, it's sort of a circuit. A lot of circuits are basically used in it. A lot of electronics, and then this amplifies and it sends the signal to the other station, and accordingly this base station on the earth then distributes the signal to the I should say other people or other wherever it needs to be sent. So this is the exact scenario why we need repeaters again and again in this sort of a communication system. And yeah, and this is about it. So the essential answer is 0.76 microwatts, which is very small, to be honest. So now in question 5, we are moving to question 6 now. Oh God, I'm having a headache today. I'm sorry about messing up, but I'm not feeling well today. Just give me a moment. So now in question 5, the linear antennas are replaced with Hertzian dipole. So now you have replaced the linear antenna with a Hertzian dipole antenna. So this was the linear antenna. Now it's replaced with a Hertzian dipole antenna, which is basically fed with certain alternating current, and it emits the electromagnetic waves in the free space, instead of this particular concept where the electrons are basically sloshing back and forth and it emits the electromagnetic waves. Here, essentially because of the alternating voltages, there is basically back and forth motion of these electrons. They basically radiate the electromagnetic wave. Okay, so you can just look up for the Hertzian. I think we have covered the Hertzian dipole in initial weeks of this. I guess week 4 or week 5 you can just refer to. And we need to compute the received power if it was a Hertzian dipole. So how does it change the scenario? Now, initially, how much was the directivity? It was 1.64. So now if you have, let's say, let me add a page, question 6. I think everything should remain same except that everything is basically same. So let's solve it here. So in the previous question, we now have d equals to 1.5 instead of 1.6. So if we substitute everything, then what we are going to get is the received power by the Hertzian dipole will be 0.63 microwatt. But we have to use this directivity value. So essentially, this is 0.63 microwatt. So the received power goes down. And makes sense, okay. Because earlier you had a linear antenna, and obviously the received power depends upon the effective area of this particular antenna, which is effective area of the receiving antenna. So it is going to receive at least a little bit more power than compared to that of the Hertzian dipole antenna, which is going to receive less power. Okay, and it also depends upon the directivity. The directivity factor is lower here. So the directivity factor for the Hertzian dipole is less than that of the linear antenna. So it also depends on that. So if the directivity is essentially going to fall, then your received power is going to lower. So that's why you see a minute change in the decrease in the received power. Now in question 5, the same question, what is the maximum effective area of the receiving antenna? So basically the maximum effective area of the receiving antenna we need to compute. And for that, we know that maximum effective area of the receiving antenna is basically lambda square directivity divided by 4 pi. And everything we have given, and it comes basically from the antenna theory. It is basically linking the directivity and the aperture area. Okay, and uh, and essentially what you have to use d equals to 1.64. You have to use frequency as 300 megahertz, which is the wavelength of 1 meters. And when you compute it, you get the effective area to be 1 square into 1.64 divided by 4 into 3.14. You solve this, you get around 0.13 meters square. So this is the effective maximum effective area of this. So this is 0.13 meters square is the maximum effective area of the by talking about the receiving antenna. Okay, so now moving on to question 8. The receiving antenna is located 100 meters away from transmitting antenna. Now you have reduced the distance. So this is 100 meters around, this is 0.1 kilometers. So that is basically 100 meters. If the effective area of receiving antenna is 500 centimeters square, so it is saying that effective area here is 500 centimeters square. That means it's 500 into 10 to the power minus 4 meters square, which is around 5 into 10 to the power minus 2 meters square. So this is the receiving effective area of the receiving antenna. And the power density at receiving location this is power density because it's power per unit area. So the power density is also given. Let's write PD as power density at the receiving side is given as 2 milliwatts per meter square. That means for every square meter, it's receiving 2 milliwatts. Okay, so if you multiply it with area, you should essentially get it the power density. Okay, so essentially your what do you need to compute? The total received power. Okay, that's pretty easy because if you have the power density and you multiply the power density with the effective cross section, which is 5 into 10 to the power minus 2, you should get the received power. So the received power will be basically power density will be essentially this particular thing because here it's meter square, meter square will go, it will be received power. So you have 2 into 10 to the power minus 3 watts per meter square into 5 into 10 to the power minus 2 meter square. This goes, so you get 10 into 10 to the power minus 5, which is around 10 to the power minus 4 watts. So it is roughly 0.1 milliwatts. So that is exactly the, oops, did we do a mistake? Yep, you can write 0.1 milliwatts as 100 microwatts. This is the exact answer of the question. Okay, just give me a moment, I'll be back. So now what do we have? For the two-element linear antenna separated by a distance of lambda. So now you have a linear antenna, but there are multiple radiating elements. So this is something called as two-element radiating antenna. It can have multiple elements. Essentially, in the practical scenario, there are something called as phased array antennas. Something called as phased array antennas. I think I've talked about this phased array antenna in week first in a very sort of a detailed manner. And you can have a lot of these antenna elements that individually emit the electromagnetic wave, and then the electromagnetic waves are emitting. Then, based upon the phase differences, these electromagnetic waves can interfere, and they can cause basically destructive constructive interference, and it can basically direct the beam in certain directions. So it's basically a concept of beam directivity based upon the phase differences. Now, what's basically the concept is that for the two element linear antenna separated by distance lambda. So let's say this distance is lambda. So this is the distance of the order of wavelength, and it's necessary because if it's less than wavelength, then there will be essentially diffraction, and it'll be less than the wavelength, and there will be diffraction and other second order phenomena that's going to take place. So once you have the two element linear antenna that is separated by the distance t, you talk about something called as AF, which is basically the array factor. And I talked about the array factor in the beginning, that it represents the geometry and essentially takes into consideration the excitation of multiple antennas, which basically modify the radiation pattern. So essentially you have each of the element, let's say this is element 1, this is 2, this is 3. So each of these is separately excited by their sources, or it can have a common source of excitation. Source of excitation. And the source of excitation can be an AC source that is going to excite each of these antennas. And essentially, once this one emits an electromagnetic wave, similarly this one, similarly this, the other one. And when you know that the electromagnetic wave is emitted, it is emitted in sort of a spherical symmetry pattern. And all of those electromagnetic waves are basically emitted here. And they form basically the interference pattern. And because of that, there is constructive interference, there is destructive interference. What does it result? It results in basically cancellation of the waves in certain directions. It results in boosting of the waves in certain other directions, because that's what interference does. Okay. And now the concept is that how can you use for your benefit? God. So that's basically the concept of something called as phased array antennas also. And it's also the antennas. It also is something called as beam steering or beam forming or whatever you name it. So essentially the concept is that if you have a linear antenna, then these are the multiple elements of this linear antenna. And if this is emitting electromagnetic wave like this is emitting like this, and if you want these electromagnetic waves to go in this particular direction, let's say at a towards theta equals to 45 degree, you want the directionality to be maximum in this direction, you want the lobe to be maximum in this pattern. How can you basically tune it without basically turning the linear antenna? So you don't want to turn it like this, you don't want to make the antenna go like this. And essentially, when you turn the antenna, it will naturally go in this direction. The electromagnetic waves will go in this direction. But you don't want to do this. You don't want to touch the antenna itself. You just want to do some magical trick with the electromagnetic waves so that they can basically steer or get directed towards a particular direction. So that's essentially the concept of this, I should say, beam steering. So what you do is basically you give the excitation, and you give a different excitation with different phases. Okay, so essentially you give a excitation of 0.1 pi. I'm just assuming some numbers. Let's say you give a 0.4 pi, 0.6 pi. And because there is different phase differences between the excitations, that will basically get reflected in the electromagnetic waves itself. So essentially, when the electromagnetic wave will be radiated, it will be having a certain phase difference of 0.1 pi. So from this, it will be having 0.4 pi. From this, it will be having 0.6 pi. So it's as if let's say the first wave was emitted something like this, and the second wave was emitted, let's say, something like this, and the third wave was emitted, let's say, maybe something like this. It's just roughly assuming. It's basically a phase difference of pi, but I'm just saying, assuming. I'm not drawing it to the scale. So essentially, you see that once it happens, the crust of this is falling on the trough of this, so this and this can cancel each other, but the crust of this is exactly like falling on the crust of this, so they can basically add. So these two waves can add, these two waves can destructively interfere, and accordingly, you have so many of these electromagnetic waves now because you have so many linear arrays basically. So what happens because of these constructive and destructive interferences? You have essentially cancelled the beam in certain directions. So this and this cancels. It's basically canceling in the space itself. So you have cancelled its effect in the free space, but you cannot just, the energy cannot just vanish. The energy has to be directed in different directions. So that particular energy gets directed in this particular direction. And essentially you have the beam steered to be to along this particular direction. So the beam gets steered along this direction, and in the blue regions, all of the electromagnetic waves basically cancel. They form a, they get destructively interfered. So this is sort of a destructive interference. So the green one is basically constructive interference. The blue one is basically destructive interference. This is destructive interference. And finally, you get a beam which is basically steered in this particular direction. So this is exactly what's happening, what is done in radars, drones, anti-drone systems, missiles, and all of these defense-related stuff. It's most of them is based on this particular concept. And just the layman concept of it, it's also deeply involved in it. Now, what do we have to essentially see here? The array factor you might have talked about, it depends upon, and it depends upon the spacing. This array factor, basically, what you write, it depends upon the spacing between the two elements. It depends upon the relative phase difference between the two elements, delta phi. It depends upon how many elements are there. This is element 1, 2, 3, 4, 5, so on. So it depends upon the number of elements. And it depends upon the observation angle, at what angle you are basically observing the output from this particular array of an antenna. Okay, now essentially what you have is basically an array factor which is equivalent to cos of half of kd cos phi sine theta plus alpha, and all of these terms you know. And here in this particular question, we have t to be equivalent to lambda, which is basically the spacing between the two elements. And alpha is equivalent to 0. I guess it's given. Yeah, it's given. Theta is equivalent to 90 degree. That means it's radiating in a lobe like this. So if you have a spherical symmetry of the antenna, this is theta. So this is theta equals to 90. So this is theta equals to 90 degrees. So I have a lobe like this. And what else? And the wave number is, you know that it's 2 pi over lambda. So KD is essentially 2 pi over lambda into lambda. So it's KD is 2 pi. So KD you can write as 2 pi. Everything is given. You can compute the array factor as cos of half of 2 pi. How much is phi? Cos of phi. I guess cos of phi needs to be computed. Sine theta is 90 degrees, so it will be 1. Alpha is 0, so that'll be it. So it will be essentially cos of pi cos phi. So this is exactly the I should say array factor, which is basically depending upon the angle phi. So this is the angle phi. And now what do we need to basically see? We need to see the resultant pattern. So essentially at phi equals to 0, what do you have? You need to put certain values in it, okay, in order to understand it. So when phi equals to 0, phi equals to 0, this will be 1, so you have cos of pi. So you have cos of pi, that will be equivalent to how much it will be? It will be essentially, but you need to take the magnitude, so it will be essentially for phi equals to 0, you have the AF to be equivalent to 1. For phi equals to 90 degrees, you have AF to be again equivalent to 1. Okay. For phi equals to 180 degrees, you have AF to be equivalent to, I should say, 1. And for phi equals to 270 degrees, you have AF to be equivalent to 1. What is happening? So you have the AF to be constant. That means this is 1 here, 1 here, 1 here, 1 here, along all the directions. So essentially it forms like a circle. And so the answer of this question is C. Give me a moment. So essentially you have cos of pi. So for phi equals to 90 degrees, you have cos of this is 0. So you have cos of 0, that is 1. Okay, that makes sense. So essentially you have cos of pi, cos of 0, you have cos of pi, cos 0 is 1. So you have cos of pi, so it will be basically 1. So you need to take the magnitude, it will be essentially minus 1. So it'll be 1 minus 1, 1 minus 1. That is basically, this is 1, this is 1, this is minus 1, this is minus 1. So that's what it means, yeah. So it will be exactly this pattern. So you need to basically use different values of the phi in order to compute the factor, which is basically the array factor. Now what else? What else? What else? Yep, it's the magnitude. As I told you, it's the magnitude. Essentially, it's the magnitude of this particular quantity. So that's why you need to take this as 1. It doesn't make sense to take it as -1, but you can just understand it. And this is not exactly, this is phi values. I mean, at certain angles, you are changing the phi. Okay, so now for the two element linear array separated by a distance, we are only considering two element, by the way, two element linear array. So it's a two element linear array, and this again separated by distance of lambda, and carrying a current of I1 and I2 e to the power minus j alpha. So there is a phase difference between the currents, essentially what I told you. And alpha is equivalent to pi, theta is equivalent to 90 degrees. What you need to find is the resultant array factor pattern. How you will do it? Again, if you use alpha equals to pi, theta equals to 90, d equals to lambda, so you get array factor to be equivalent to cos of magnitude of cos of pi, cos of phi plus pi by 2. Because alpha is pi by 2, sine theta is 1, kd is basically the same. It's kd will be equivalent to 2 pi over lambda into lambda, so it will be 2 times pi. And phi is basically the phi is basically what we need to essentially understand to understand the pattern. And there is half here, when there's 1 by 2 here, so this 2 and 2 will go, so it'll be pi. This is the exact AF equation. Now again, for phi equals to 0, your AF will come out to be 0. Why? Because you have cos of pi, cos of 0 will be 1 plus pi by 2. It'll be cos of pi plus pi by 2. It'll be cos of 3 pi by 2. Well, that come out to be 0. It's sort of a multiples of the pi by 2, and essentially it will be 0. So again, for phi equals to 90 degrees, you get AF to be equivalent to 0. phi equals to 270 degrees, you get AF to be equivalent to 0. When you check it, just cross check it. Phi equals to 180 degree, you get AF to be equivalent to 0. So your AF is 0, that means it's at the origin. The array factor is basically at origin, and it's basically this is the answer of this question. So the resultant pattern is something it's sort of a localized at the origin. It's basically not I should say transmitting in a lobe fashion. Okay, so this is the exact answer of this question. And essentially we are done with this particular session, which is very small because the questions were pretty much straightforward depending upon the formulas and certain concepts I discussed. And in the next week, which is week 8, I will be talking about the lasers. I guess it's about lasers, which is basically a light source, but it is an electromagnetic wave, coherent light source. So we will be talking about, I guess, lasers. We'll be talking about diffractions, and essentially that will be an important week. So if you have any questions, you can just stay. Otherwise, we are pretty much done for this session.